Euler. That's what this word is right here, Euler. It's Euler. And I know a lot of you will want to say Euler, and even later in the future you'll see it and you'll still want to call it Euler. And it's not, and it rhymes with Bueller, like Ferris Bueller, but it's not Bueller or Euler, it's Euler. Okay? So, this is a famous mathematician who accomplished a ton of math in his lifetime, and he is very famous for all of his work. But one of the things that he accomplished is some graphing theory that we're going to look at today, continuing on with edges and vertices that we talked about earlier in the week. And one thing that he did is called an Euler Path. Okay? So, if I can get my pen to work. There we go. Okay, so an Euler path is a path that travels through every edge of a graph once and only once. Also, in an Euler path, each edge must be traveled and no edge can be retraced. So each edge must be traveled and no edge can be retraced. So along with that, in an Euler path is an Euler circuit. Same idea. Okay? An Euler circuit is a circuit that travels through every edge of a graph once and only once. And like all circuits, an Euler circuit must begin and end at the same vertex. Note that every Euler circuit is an Euler path, but the reverse, every Euler path is not an Euler circuit. Okay? So, we have a little graph here. And I want to look at and see if there's an Euler circuit in this one. All right? So, let's look at this one and see if we can come up with the Euler, not circuit, I'm sorry, the Euler path. I can go from A to B as my first mode of transportation. I'm going to mark that with a 1 just to say that's the first place I went across. And I'm also going to put a little arrow in it just saying that's the direction I'm starting. Okay? Now, from B, I can go in many different directions. I can go to C, I can go to E, I can go to D. Doesn't really matter. So which way do you think I should go? Go to E? Go to C, okay? Well, that would be number 2 then. Okay? And then from C, there's only one direction I can go, and that's to E. And the reason I can only go that way is I've already gone on this edge from B to C. I can't use it again. So this will be step 3. Okay? Now, I can go from E, I can go to F, D, or B. Go to B? Okay. B. That'll be 4. The only way I can go out from B is to D. That has to be 5. Now which way? E. Okay. 6, and then 7, then 8, and then 9. Okay? That is an Euler path. We used every edge once. Okay? Now, if I wanted to make this an Euler circuit, I really need to make a bridge going from G to A. If I did that, that would be our 10th one, right? So that would become an Euler circuit. So in order to write down these, if I were to write these on, like if it asked you to write down the circuit, this is how you refer to it on your paper. You would start at A, so it would be A, comma, B. Then the next place I went was C, then E, B, D, E, F, D, G. That was the path. The circuit would have been the same thing, but with the addition of back to A again. And notice how I'm just separating the vertices by a comma. It was an Euler circuit. Okay, let's talk a moment about Euler's theorem. The following statements are true for connected graphs. If a graph has exactly two odd vertices, sorry, it's a small line to write in, two odd vertices, then it has at least one Euler path, but no Euler circuit. Each Euler path must start at one of the odd vertices and end at the other odd vertex. So that's going to give you a big clue when you're trying to come up with your Euler path. You've got to start at one of the odd ones and end at the other. A vertex with odd edges. Okay? If a graph has no odd vertices, then it has at least one Euler circuit, which by definition is also an Euler path. An Euler circuit can start and end at any vertex. If a graph has more than two odd vertices, then it has no Euler paths and no Euler circuits. Okay? So we're going to put that little theorem to test here. Let's look at these two graphs. Let's look at the one on the left first. Tell me, which one of the which vertex has an odd number of edges coming to it? B? I count 1, 2, 3, 4 in that one. E, yep, that's definitely an odd vertex. What's another one? D. Okay. Is there any other ones in here? No. Nope. So there's got two odd vertices. That tells us what? There's one Euler path, but no circuit. Okay? So we need to start where? What does it say where we start? We could start, we need to start at one of the odd vertices and end at the other. Okay? So if I start at D, doesn't matter which way I go from there? We'll go to C first? Okay, let's try that. So D to C, that would be our first step. Okay? Where else can we go from C? We got three other choices. E or A? Okay, so let's just do A. That'd be 2. A, I don't have a choice but to go to B. That's 3. And then let's go to D. That's 4. E is 5. Can go to C again. 6. 7. And then 8. So there's probably several different ways of doing this. We started at D. Then we went to C, A, B, D, E, C, B, E, right? So that is our Euler path on that one. Look at the right graph. Do we have any odd vertices in this one? No. So what does that tell us by Euler's theorem? Won't be, but it's a specific thing. What does it say? No odd vertices. Then there has to be at least one Euler circuit. Okay? And you can start at any vertex. Doesn't matter which one you want to start at. So which vertex do you guys want to start at in this one? U? Okay, we'll start here. So that means we've got to end here. All right? So go U to O. That's 1. Let's go O to M is 2. 3. 4. Where should I go now? Huh? You said O or V? It doesn't matter to me. Okay, so we'll do 5. 6. Now we don't want to go back to U already. We got to end with that one. 7. 8. 9. 10. 11. 12. 13. And then back to U again. That's 14. All right. So once again, if we were going to write this out, our circuit would be U, O, M, N, P, O, Q, R, P, V, R, T, S, I'm running out of room, Q, and then R again. Okay? So notice that I'm marking them as I go. I'm labeling them with a number so I can go back and be able to write down my circuit easily by just following my path. You need to have some way of doing that while you're doing this, because if you don't, you'll lose and you'll forget which way you went. It's kind of writing a maze. You know, you have to draw it as you go. Okay? So, an application. One application that I can think of is there's a mansion up in Duluth that we toured. There was a murder that was done there, and I can't remember the name of the mansion. Okay. Yeah, So it's a big mansion. It's beautiful. And one of the things is that when you're planning a tour of a mansion, you might want to plan somehow of making an Euler path going through it so you can go through all the rooms and check out the rooms. That's a good question. Or a circuit. It could be either one. Yes?
People think I'm related to them, but I'm not, because my name sounds related.
Oh, yeah, it is similar. But so in order to do this, when you're taking groups of people through a tour, you don't want to have to go through a doorway at the same time with the other group. It makes a bottleneck. So an application of this is, how would you plan a tour through a house in which you don't go through the same doorway twice? Okay?
How would you go in?
Well, some rooms you'd peek in. You wouldn't actually go into it. Some rooms only have one door, right? In the case that we have here, we have rooms, and all of the rooms have more than one door. Okay? So is there a way to find a path that goes through each door once? The other thing is, when you go outside the house, you can only go to E. You can't go from C to A outside. That's another rule in this case. Okay? So here I made a little graph of all the points, being A is one vertex, B, C, D, and then E is the outside point. Okay? So first of all, let's draw our graph. I can go easily from A to C to D to B to A again, because they all have these doors, right? Yeah, we're not there yet. We got to still draw the map. Okay, so I know I can get inside the house from one room to the other. So now each room has a door to the outside that I can connect to E. A has 2 of them. So I'm going to draw 2 paths to E. C also has 2 of them. Okay? B has 1. And D has 1. Okay? So we have all these edges. Now we need to go through and count how many odd vertices we have. Okay? D is obviously an odd vertex. D is an odd vertex. I meant to make that in green, and it didn't work for me. Because 1, 2, 3 edges coming from it. Okay, 3 is an odd number. What's another one that's an odd vertex? A, let's count them. 1, 2, 3, 4. I see 4 edges coming out of A.
Oh, B.
B, yep. E has 1, 2, 3, 4, 5, 6 edges coming out of it, so that's even. C has 1, 2, 3, 4 edges, so really these are only 2. And that tells us what by Euler theorem? There's one path. Okay, at least one path going through this. So we start at one odd vertex and end at the other. All right, so say I start with B. I could draw 1, and I can go any which way I wanted to from this way. I can go up to E, that could be 2, back down 3. I could go down to C, that would be 4. Then back out to E again, 5. Back in is 6. Go across to D is 7. Out to E again, 8. Back in, 9, and then end at D, 10. You guys will be able to find several paths to this, okay? Flurry's algorithm makes me think of a flurry that you can buy. I need some ice cream and some chocolate chip cookies mixed together, right? But anyway, if Euler's theorem indicates the existence of an Euler path or an Euler circuit, one can be found by using the following procedure. So instead of just guessing and checking, there are some ways of making it a little easier for you to find it so it won't take you so much time. So I'm going to share these with you so you can use them for your homework. Okay, if a graph has exactly 2 odd vertices and therefore an Euler path, choose one of the 2 odd vertices choose one odd vertex as a starting point. Okay? If the graph has no odd vertices and therefore a Euler circuit, you can choose any vertex. And that's nothing new. We talked about that already up above at Euler's theorem. But this is what is new right here in part 2. Number edges as you trace through the graph according to the following rules. Okay, after you've traveled over an edge, you can erase it. I don't. I just use another color pencil, or you give it a label, give it a number. Okay? This is because you must travel each edge exactly once. They say show the erased edges as dashed lines. That's whatever, but I use color pencils. I think that's easier. Okay, the second point on this, and this is where it really gets helpful. When faced with a choice of edges to trace, choose the edge that is not a bridge. Okay, because if you erase that edge, you can never go back to the other part of the graph. You've disconnected yourself. So you don't want to disconnect from finishing off the other part of the graph. Travel over an edge that is a bridge only if there is no alternative. Okay? So here I have an example I want to go through. And we want to ask ourselves if it's a bridge or not as we go along. Okay? So on this one, the odd vertices are F is one of them. And C is another. Is there any other ones that I missed? No. Okay. So let's start off at one of those vertices. Which one should we start? Doesn't matter to me. F? Okay, so going to F. I could go to D, B, or E. Which way? B? Okay, so I'm going to go this way. That's my first one. Okay, now I'm at B, and I only have one choice here. So obviously I have to go to D. There's no other option on that one. Okay, now at D, I have three choices. I have going to A, C, or F. Are any of those bridges? No, so really I could go any of them. It doesn't matter. A bridge is something that, like here. If I were to cut this off, I would be stuck on one side or the other. I wouldn't be able to go. So that's a bridge. Okay? So D, I could go to A, C, or F. Doesn't matter. So we'll go to A just for fun. That's 3. And then A to C is 4. Now I'm at C. Do I have any bridges there? No, so I could go either way. So this, I'll go this way. 5. You could go the other way. It doesn't matter. 6, 7, and 8. So I really didn't have to deal with bridges in this one, the way we went. Yeah, you have to end at an odd vertex. Yep. So here's your assignment for today. All right. You guys can work on that now.